Good thing I checked. Otherwise, it becomes silent movie, right? Okay, so I'll just fix the indentations first, because even though it's not strictly required, it is still much better that way because I can tell which one is embedded into which one. And then I'll just add the pound sign to each line, like that. And now we can start the actual writing of the program. Okay, how many variables do we need in this program? Two. Okay, so we go to the data section. We have count as a 4-byte or 32-bit counter. So that's just a .int. It doesn't matter whether you initialize to 0 or not, because I think it's a better approach to initialize it in the code, so that you do not rely on the variable getting initialized to begin with. And then we have the character. So in terms of buffer, we really only need one character in this case. So .fill1 or .byte0 or something along that line is enough to give me that 1 byte of buffer. Then we can switch back to the text section and do a .global _ start, and then we can start with the actual program. Okay, count getting initialized to 0. That's pretty easy. We can just do a move L $0 into count. Okay, just because it fits the width of that one instruction. And now we have a loop. Every time you have a loop, it is usually good to put a label before, at the very beginning of the entire loop, and one label at the very end. Now this is a do-while loop, which makes it a little bit easy. You only need one label at the beginning. You don't really need a label later on. I will do it, in a fairly clumsy way. In other words, I will do it in a way to match the exact pseudocode, because there are ways to shortcut it. Okay, you can jump out from the conditional statement. But I'm not going to do that. I'll just do everything as described by the pseudocode. Yep.
If I don't have the initial line, but I do have the pound. And then
that'll be fine. Yeah, that's okay. But in general, it's better to have your own initialization in the code itself rather than relying on the initialized variable here. Because if you want to turn this into a subroutine, then having the code to initialize the variable is a better approach. Okay, so the first thing I want to do is to try to read a character from standard in into ch. So that means I have to set up all the registers. 3 into EAX to request a file read operation. We move $0 into EBX to mean we are reading from standard in. We move the address of the buffer into ECX, because that's the address where I want to put that 1 byte. And EDX is 1, because I want to read up to 1 byte. And then we ask the operating system to perform the operation. So are there any questions about the program up to this point? The questions? Yep.
You put read a char from standard in into CH. Was CH just your buffer label?
Yeah.
So
yeah, I guess I should change that.
Labeled it CH because I thought that's what wasn't sure if something weird.
Okay, that was all done.
Oh.
Global replace, yes. So now it's all CH, no buffer. They mean exactly the same thing.
Okay,
right?
that's what I figured.
That's okay, that's cool. Okay, now I want to see if a character was actually read. So I have to look at EAX, because EAX tells me how many characters was actually read. I ask the operating system to read up to 1 byte. If the operating system comes back and say it could not read anything, I'm at end of file. So that's basically what I will be checking here. I have to compare. There's no way to shortcut this one. You do have to compare EAX to 0. And I would say if it is 0, I would jump around the entire block of conditional statements, and we'll just go all the way to this part here. And this part would be, I called it end if 1. Okay, so if I do not go to end if 1, that means EAX is non-zero, which means it must have read exactly 1 byte. So it's time to compare and see whether that 1 byte is the space character or not. So here, I would use the same approach. I would compare byte this time. Now, the width of operation is very, very important. Because if you use compare long here, or just compare, which implies long, the program will work sometimes and not work other times. It depends on how many bytes you actually allocate for the buffer. If you only allocate 1 byte for the buffer, and there are additional variables after that, and you do a compare long here, it will pick up the beginning of the next variable as a part of the 32-bit integer that you're comparing. So that that won't work. On the other hand, if there's nothing after ch, like in this case, it will still work if I do a compare long, even though it should not have worked in this case. So you have to pay attention. In this program, it does not matter because most people use ch as the second variable and therefore avoid that problem altogether. But if you have a different program with more variables after ch, then you can potentially have a problem. So compare byte is what you want, and we want to compare that to the ASCII code of the space character. You can just put 32, which is go ahead.
So you can assume that memory that you don't allocate is automatically 0?
It is not a good assumption, but in this case, it is initialized to 0. Okay, but it's not a very safe assumption because this is the first time we run the program. If I run this code again without reloading the program, then potentially the other parts of memory can be corrupted already or can be changed. You cannot. It's not safe to assume it is all 0 to begin with. It's just that in this case, they are in zeros. And we can compare this to ch directly because we can have up to 1 memory operand. So we can, in this case, I will just use up that 1 memory operand to compare to the ASCII code of the space. And I would say if they're not the same, then go around the conditional statement. So I'll go to end if 2, and I immediately write down where my end if 2 is, so that I don't forget where I'm supposed to put the label. And inside the conditional statement, all I have to do is to increment count by 1. And once again, since I can use up to 1 memory operand, I will just use that here by saying add $1 to count. Because count is a direct operand, it is a memory operand. So this saves me the trouble of having to move stuff between registers and back to memory and stuff like that. And there's one more thing to do. We have to implement the end while, or the end of the do while statement. So over here, okay, yep, go ahead. Yeah, we have to jump back to the beginning, but only if I actually read a character. Okay, so here we have a little bit of a problem. Well, I wouldn't call that a problem. I think we are still good here. So we just have to do another compare, which is redundant. Remember, I wrote this program in a way to mirror the high-level logic and not do it in an actual optimal fashion. So over here, since I'm matching the overall code to begin with, I will actually have to do another compare long 0 to EAX. And if it is non-zero, then we go back to the beginning of the do loop here. And remember, this is non-optimal. Okay, I'm just doing it so that it matches the logic of the pseudocode, and not doing it, in a shortcut way. And that should be it, I think. Well, if it doesn't work, I'll know. Yep.
Can you just declare 32 bytes and then just use compare long, just in case?
It is not safe to do so. You should always make sure that your operands match exactly what you need to compare.
Yeah, okay, so it's for
Because what happens, well, what if you use the same buffer for some other read operations, and those read operations will read multiple bytes? You see what I mean? You can declare buffer to have 32 bytes. In this case, since you're only reading 1 at a time, and everything else are initialized to 0, yes, you can use compare long. But that's basically, abusing, the fact that you are allocating more bytes than you need, and it is also based on the unsafe assumption that nowhere else in the program those bytes will be altered. If you use the buffer, for anything else, and they can potentially read multiple bytes, then the assumption is wrong. Now, this code works, because it is on its own, and there are no additional code to mess up the buffer. But when you extend the program to deal with other stuff and put other stuff into the buffer, will you remember to come back and change this instruction to make it work again? That's the question. Probably not. Okay, so I always try to make sure that I do not rely on anything like that. I make sure my code will work regardless of the rest of the program. I won't take any points off if you do a compare long and you just allocate more bytes. It's just that in general, it's not a very good approach to do it that way. So here's checkpoint. After checkpoint, I will exit the program. So we just have to load a 0, 1 into EAX, a 0 into EBX, and then we ask the operating system to get this program exited. Are there any questions? Yep.
Is that fine if we put checkpoint? Because on your assignment you said we had to put check here.
Oh, check here is good. Okay, fine. We'll change it to
How
check
about
here.
if we put checkpoint? I put checkpoint up here.
Well, then we'll ding some points.
Not too much, not too many.
You didn't even put it there. How can you ding everyone else for not doing it?
Well, because it is your homework assignment. I'm just here to show them how it is done.
If his script can't do it and he has to do it manually, he's going to take points off. So if you didn't put check here, his script can't do it.
It's consider cost of labor.
I thought we already paid for that.
Oh, that's just the heating and cooling of the room.
Well, the heating's getting wasted. The window's open.
Can anyone close that? I mean, do we have a stick long enough to close it?
Is there really a window?
I hope I won't break it. Then it will just be really, really open, right?
Can we get a tall person
Sort
in
of.
here?
It's kind of spring loaded, unfortunately.
Yeah, both of them were open.
Yeah, I think. Okay, thank you.
Yeah, the other one's open too.
That's harder.
Next time I bring my foam seal, just seal it too.
Just bring some caulk.
Hmm?
Just bring some caulk.
No, I have the expanding type. The foam expanding type. Yeah, that would
It's
make a
like
big mess too.
Fancy caulk.
Fancy cough, yes. Let's see. So we have the program ready to run, so we'll go ahead and make a test file first. So we have a test file, we'll call that test.in. And we'll just put in 4 spaces.
What's the RFC specification for an in file?
I don't know. What is it?
You're using it.
Yeah, it doesn't matter. Okay, we put a breakpoint at check here, I think. And then we run the program. And before we run the program, we have to redirect the input from test.in. And the program is all done. I take a look at, print count, and it is 4. Program is good. Okay. Now this is only one test case. The other test case is I want to create an empty file. Okay. Create an empty file, and then it should exit the loop, and then count should be 0 in that case. So we'll have to double check that one too. So GDB spaces. Once again, put a breakpoint at check here. Run the program, and this time redirect from the empty file. And at least the program exited. Okay, some programs may enter an infinite loop if it is not done correctly. And if I print count, it is initialized to 0. It is still 0. Okay. Are there any questions about the process of writing the program in assembly?
I have a question. What is it that keeps it? Because we didn't have to implement anything to tell it after it had read like the first character to go on the next time it goes through the loop and to read the second character. It somehow seemed to automatically know to do that.
Yes, because it has the same mechanism as cin. When you use cin to read something from standard in, you never have to tell cin and say advance, this many bytes, because as you read, the file pointer advances, automatically. And that's a typical file operation. When you read, it will automatically move the file pointer along. Okay. Any other questions? Yep.
I had an issue where it was getting hung up on the end line, on the number 10.
Line feed.
Line feed. Yeah, it would not.
When you do it interactively.
No.
When you put
GDB.
in. Through GDB, but that's interactive. When you run the program without the redirection, that is still interactive. I can show you what I mean by that. So if you set up okay, we'll just go ahead and set up the breakpoint just like last time. And this time I'll run the program, manually without redirecting, and I can give it like this is a line, and press the enter key. It comes back and asks me again because it is the program would have run already. Count at this point should be 1, 2, 3. Count should be 3, but I cannot stop the program just yet because I have to indicate end of file first so that the program will terminate. It will get out of the loop. So what you need in this case is to press Control D, which is end of file. When you press Control D in the interactive mode, it is the same as saying, okay, this is the end of file for standing in.
I wasn't doing any of that. All I did was redirect it to the file.
Oh,
and
really?
I redirected it to the file, and basically after the last space, there was a character, and then there were 2 line feeds. There were 2 10
Okay.
on the ASCII thing.
Yeah.
And I kept running. There were only 2 of them, and my program basically should reset, go back, read it through. So it should have gone through twice, recognize the 2 of them, and then move past, and they would not move past. It just kept going back, going back.
You may be jumping back to the wrong point so that it skipped the reading part.
I jumped back to the same point that it worked for all the other things. So I don't know why.
Okay. Well, you can send me your test file, and I can see what this program will do to it. But I think this program will work regardless. I mean, the only time this program will not work is when you feed it a file that has no end.
Let's try that.
You'll just run into an infinite loop, and the counter will. Well, the counter won't even count if you feed it like /def/0. Okay, so that's it. This is the previous homework assignment, and just to keep you guys practicing all this stuff here, which will come in handy later on. You have your current homework assignment, which is about the same thing. It's just a slight variation on the same theme. So this time I want you to read in a number and convert it into, basically you want to interpret a hexadecimal number and get the value and put it into a variable. But you don't have to worry about the logic. I got the logic part done already. You just have to implement the logic. So here's the program. First thing is we have a 32-bit unsigned integer n, and then we have a Boolean variable called n of input. How do we implement a Boolean variable in assembly? Okay, 1 byte would do it, all right? Dot byte in assembly.
Did the attendant?
Oh, thanks for asking.
No problem.
And you can see the logic of the program is about the same. We try to read the character from cin, from cin, standard in into ch into the character buffer. But the logic is a little bit different. It looks kind of complicated, but it really is not that complicated. The first thing we want to do is to check, did we actually read a character? If we did, then we can process that 1 character. If we did not, then we'll just go ahead and say, oh, it is time to quit the loop and set the flag true. And when we check the flag at the end, this will get us out of the loop. On the other hand, if we did read a character, then we have to go through these cases. Did I read a character between 0 and 9? So you have to find either the ASCII code of 0 to 9, or you can just put quote 0 quote. That will do exactly the same thing. If it is within 0 to 9, then you want to perform this calculation and update n in the process. If ch is between a and f, then I got this part wrong, didn't I? It's a bad thing when I make mistakes, but it's a good thing when I can catch it right away. Okay, I forgot the +10 here. Okay, there we go. Yep.
Sorry about I was late, but can I please see the solution to the homework? Just glance at it real quick.
No, I have to keep moving because we are already behind schedule for this class.
Oh, yeah,
so unless we want to compress the end of the semester, like Okay. Okay. Well, I'm going to upload the files, and also there's a video recording anyway, so you can always check it back later.
Yeah,
Okay.
of course.
Okay. So in this case, do we know how to do some calculations like this in assembly? You just have to kind of break it up into the appropriate parts. Okay. So I'll just kind of take this one here and use a text editor to illustrate how to do this one. So you might want to. I don't think you guys have any problems with this anymore because of the first exam. Okay, if you know how to multiply by 73, multiply by 16 is like easy, right?
Is there an instruction for that?
Just teach us the bolt command.
The bolt command. There's a mode command. The mode command is it seems very convenient, but there's a pitfall of the mode command that will get most people. Okay, so we'll just do it the hard way. So when you look at this instruction here, you can break it down into n multiply equals 2, n multiply equals 2, n multiply equals 2, n multiply equals 2. That will take care of the multiply by 16. Then you have n plus equal to ch, and n minus equal the ASCII code of 0, and you're done. Okay? Now, this part here, this one here is equivalent to n plus equals n. In other words, we don't really need multiplication. We can just do everything with addition and subtraction. But you guys know that already, don't you? Very good. So, getting back to here. This one is just slightly more complicated. And you just have to make sure that you add the 10 after you perform the subtraction, because the letter A means the value of 10. So you cannot just subtract the ASCII code of A from the ASCII code of A, because that will give you 0. We want that to be 10. So that's why it's a little bit different from the previous one. If it is a character that is not 0 to 9 or A to F, we just consider that n of the input. Okay, so that makes validation really easy, because anything that is not a proper hexadecimal digit, we just say, okay, we have seen the end of this entire thing. And when you get out of the conditional statement, all you have to do is to check whether n of input is true or not. If n of input is false, then you go back to the beginning. If n of input is true, then you exit the loop and get to checkpoint, which is the label that you have to stop at. That my script will stop and then check whether you got the right input or not. Are there any questions about this homework assignment? Structurally speaking, it is almost the same as the previous one, except when you process the character that you have read, this one is just a little bit more complicated. I don't think it's significant. Yep.
The body of the first if, is it
the body
CH?
of
The body of the first if?
You mean the outer if?
The inner if.
Inner if. Okay.
Okay. And is it the CH minus O or minus 0?
That's a 0.
0.
Yep. It wouldn't make sense if that was a O. Yep.
I just want to make sure the multiply by 16 and all the addition stuff, that's to turn the ASCII value of the hex digit into the hex value of it.
This part is. This is the conversion. It converts the ASCII code into the value that the ASCII code is representing.
Why do we multiply by 16 then?
Because you are seeing another digit in a hexadecimal number, so you have to multiply whatever you know already by 16, and then you add the value of this new digit. Yep.
So what's our test data going to look like for trying this out?
Your test data is going to look like, you can just give it a file with one single line, and the simplest one is a 0. Make sure that it will still get back with a 0, and then you can say any type of thing, anything within 8 hexadecimal digits should be okay.
So it's 8 hex numbers.
Yeah, exactly. You can use that would be a valid hexadecimal number, because all the digits are from A to F or 0 to 9. And when you print n at the end, you will have to print it as a hexadecimal number so you can match it easily. And print has a way to do it in hexadecimal. I think it's just print /x, then it will print the number in hexadecimal. Yep.
So the point of the program is to convert from hexadecimal.
Yep. It's not converting into hexadecimal. It is actually reading a hexadecimal. It's interpreting a hexadecimal number from the input file into the internal representation of whatever base you use. It's just reading a hexadecimal number, and so that your variable n will end up with exactly that value. Yep.
Do we need to check whether we are reading up to 8 digits?
No, you don't have to check. In the homework assignment, I also say that you can assume that input will not overflow a 32-bit integer. So I make sure that my test cases will not, exceed 32 bits. If it does, it will just move the more significant bytes out of the 32-bit integer. There was a question somewhere. Was it you? No?
Yeah,
Yes.
Can I just see the previous page? I was still copying it down.
No, we have to keep moving. We got to keep moving. Yep. It's going to be uploaded. There will be the video clip. So, I really don't want to spend the time that we cannot afford at this point.
I didn't know you had to go that long. It's my fault.
Okay. All right. So that's the new homework assignment. And guess what? You do have a gift from me, which is spaces. You can use my spaces as the base program to work on your base 16 program. Now, is it going to help or is it going to confuse you more? That's for you to decide. But I'm just saying that if you use my program as a beginning part, I will not consider that cheating or plagiarism. Exactly. Yep, exactly. That's a good point. But it seemed to work. It seemed to work with the 2 test cases that I fed it, right?
It's going to be extra credit. Without that, it's going to be extra credit. This homework is extra credit.
No, we're not getting to the extra credit part yet. Yep.
Are you requiring the presence of an end of input value label specified somewhere, or can we use a register if we want?
To do what?
End of input instead of the end of input boolean. Can we just use a register?
You can use whatever you want to get it out. I'm only testing for n.
Okay.
Yep. All right. So we are moving on to the stack now. Okay. We are pretty much all done with interrupts and system surfaces. So we are now moving on to the stack. Now this is a big topic. This is a very, very important topic because up to this point, all we could do is to write simple programs that do not have subroutines. Okay, and subroutines in assembly is just as important as subroutines in C, C++, and just about any programming language that we know. I think there are only like 1 or 2 programming languages that do not have subroutines.
I think one of them's Fortran.
Huh?
I think one of them's Fortran.
Fortran has subroutines. It has Go subs. It is not the same true subroutine that we use today, but it has the same effect, but it does not support recursion. The subroutines that we talk about in this class will support recursion because it is really just the underlying mechanism of the subroutine in C, and C can support recursion. But before we talk about subroutines, we first have to talk about the stack. Now, how many people have already how many people took cisp310 and the concept of a stack was discussed? Okay, not enough. Yes?
I took it's all about stacks in Java where you insert where you push and pop.
Yes, you push and you pop, exactly.
Push from the rear, insert from the front, pop from the rear, insert from the rear, pop from the rear.
No, you push and pop at the same front. That is the same interface. Okay, so let me just briefly describe what a stack is. Okay, a stack is a LIFO structure. It stands for last in, first out. If you have any trouble remembering what a stack is, just remember, envision a U-Haul truck with STACK, as its label. Okay, that's a stack, because when you move, the very last bicycle that you push into the truck and then slam the tailgate, immediately, will be the first thing that falls off the truck when you open the tailgate at the destination. Okay, just remember that. That means it is last in, first out. Okay. On the other hand, if you put the map of the destination as the first thing into the truck and just say, okay, let me just make sure I remember to bring the map of the destination, and that's the first thing you put into the truck, guess what? When you're lost, you will have to empty out the entire truck just to get to the map, because it is last in, first out, which means the first thing you put in is the last thing that you retrieve from the truck. Okay, so that's the concept of a stack. The concept of a stack, it seems kind of useless. I mean, it doesn't sound very exciting. It does not sound useful at all. But I can tell you already, last in, first out, the concept of a stack extends well beyond the scope of this class. For those of you who want to get into compilers, it's all about the stack. Okay, when you parse the input of a programming language, it's all about the stack. Okay, so the stack is much more important than just, in assembly language, what type of instruction do we use to push and pop. Yep.
So we're not going to use the stack or learn how to use it in this class?
Yes, that's where we're going now.
Oh, we are? I think it was beyond the scope, though. I do it.
It extends out of the scope of this class, which means we will cover the stack, but we won't cover all the uses of the stack.
Okay. Hey, all right, cool.
Yep. All right, so the first thing we want to do is to talk about the stack pointer, because this is assembly-specific stuff, okay? The stack pointer is called the ESP, or the extended stack pointer. For all we know, it's just the stack pointer, okay? The stack pointer is basically the address. It's a register, just like EAX, EBX, ECX, and EDX, but the value that it contains is special. It is the address of the next byte to remove. Okay? Or you can also interpret it as the last byte that you push onto the stack. Okay? The stack rolls down to lower addresses. In other words, when the stack is empty, the stack pointer points to a higher address. As you put more items onto the stack pointer actually gets a smaller and a smaller and a smaller value. In other words, you have to look at a stack of dishes upside down to actually see a picture of the stack that is implemented in assembly. Because when we put new stuff on, okay, let me just draw a picture here. Okay, when you go to a buffet place, and they have all those clean plates or supposedly clean plates on the counter, it's a stack, right? The first thing that they put onto the table is the last one that customers will retrieve. So in that sense, the stack, when the stack is empty, the stack pointer is all the way down here at the countertop. But as you push more stuff, as you put more plates onto the table, the stack pointer actually goes up, because this is how gravity works. Okay, but in assembly programming, in terms of memory locations, it's the opposite. Okay, so in this case, we say this is high address is pointing up. Your stack pointer is all the way up at the region that is allocated for the stack when it is empty. As you put more items on the stack pointer will move down. As you push more stuff onto the stack pointer will move down. It doesn't sound very intuitive, because in the physical world, the stack pointer goes up as you store more things into the stack. But how come in the implementation of a stack in assembly or in machine code, it moves down? Okay, it seems kind of counterintuitive, but it is there for a very, very good reason. So we'll see that reason as we use the stack pointer in this class.
So the sound seems like the ESP, the pointer, is always point to the first item in.
It points to the very last item that you store in the stack. Yep.
So you say move down in memory?
Mm-hmm.
You mean the number gets
lower
or greater?
Well, let's go ahead and actually run some instructions, and we use the debugger to illustrate this point. Okay, because the next slide talks about push and pop. Let me just kind of go through these concepts first. Just really quickly go through the concepts. To push a value, and push is actually a technical term. It is one of the operations that you can perform to a stack data structure. To push something into a stack is to basically store a value in the stack. You can look at a stack as a storage kind of device, and as you store more things, you are pushing more things into the stack. And here's the U-Haul truck example. To pop is to unload the most immediately available item from the same U-Haul truck. In other words, when you're popping, you're popping the very last item that you store in the stack. Okay. Just remember, when you go to a buffet, restaurant, when you take a plate, that's a pop operation. When people, when the waiter or the waitress at the restaurant put more clean dishes, on the stack, that's pushing. Okay, so that's one thing that you can do to remember. When you load up the U-Haul truck, it's pushing. When you unload the U-Haul truck, that's popping. So we have these individual instructions. The first instruction is the push instruction. The push instruction, for some reason, is not abbreviated to PSH. It is actually spelled out as PUSH, which is not conventional, because all the other instructions are abbreviated to MOV without the L, without the E, and so on. So this time it is just PUSH. It expects exactly one operand, and that one single operand can be any operand that we have talked about. It can be immediate, can be indirect, can be direct, can be based, can be register, can be anything that we have talked about so far. Yep.
What about the size of the operand?
That's a tricky question. Okay, the push instruction can take push W. It can push 16-bit at a time. It can also do a push L, which means it can push 32-bit at a time. But there's no push B. You cannot push a byte on the stack. Yep.
You said push W to 16, push L be 32-bit?
Yes. Okay, so that's the push instruction. Push F is another instruction, but the operand is implied. It is pushing the status flag register. The status flag register is the register that contains all the carry flag, the zero flag, the overflow flag, and the sign flag. So if you want to store, or if you want to make a copy of the status flags because you're going to do something to mess them up, but you want them back at a later time, push F is what you need to push it onto the stack so you can retrieve that later.
Push F is...
It pushes the status flag register, which has the carry, sign, overflow, and the other bits. Yep.
So you can't push an immediate?
Yes, you can. Yep. It's only because the i386 is a CISC processor, so it gives you the same flexibility as with your move, basically. With a RISC architecture, the only thing you can push is a register. Okay, and then we have push A. Push A is just a shorthand to push all the registers onto the stack.
At once? Is it like do it at once or one by one?
It does it one by one. It pushes all the registers onto the stack one by one.
Is there any order to the registers?
Yes, there's a specific order. I cannot remember the order, but I don't really recommend the use of the push A instruction because once again, it's a CISC feature again. And I'm trying to teach the class so that it will be applicable to both CISC and RISC architectures that you will encounter in the future. Yep.
So when you push an item onto the stack and then you push the flags, is it like two separate spots or is it like your item then your flags?
They are two different.
So
they will take up different places on the stack, but they will be contiguous. There's nothing in between. Okay, so the next slide talks about the pop instructions. The pop instructions are basically matching instructions relative to the push instructions. The first one is just regular pop. It can be pop W for popping a 16-bit content on the stack. It can be a pop L, which pops a 32-bit content from the stack. Now this time it expects any operand other than the immediate operand, because when you pop something from the stack, you need a place to store whatever you're popping from the stack. And immediate does not specify a place where you can store something. Okay, so any operand will work with pop except for immediate. It will work with register. It will work with any of the memory operands. Yep.
So you get to know the size of the pop.
Correct. You have to be very much aware of how many bytes you are popping. Yes.
So is it possible to pop, say, an arbitrary integer long onto the stack and then pop it out onto the flags?
Yes, you can. Yep, you can plan stuff like that. It's awesome. Wait until you get to see the call and the return. You can do really dangerous stuff with those two. Yes, yes. This is not dangerous enough. Pop F is the matching instructions for push F. If you have an earlier push F instruction to save the status flags, including the carry, the sign, the 0, and the overflow, you can use a pop-f instruction to retrieve what you pushed earlier. So you can process the flags afterwards. You can just restore, basically. Look at push as backup and look at pop as restore. That's basically what they are. Yep.
There's a pop L and pop W, right?
Yes. And then pop A, or papa, is basically, it is papa. And pop A is the matching instructions for push A. So if you have a push A instruction earlier to save all the registers, later on you can have a pop A instruction to restore the registers. If you use push A and pop A, the actual order is not important because the instructions are self-consistent. Okay? Any questions about the push and pop instructions? Yep.
Can you give us some examples?
That's
of the
exactly what I plan to do. Applications.
Of like push and pop.
Oh, there are so many applications. Every time you want to save a register because you want to use it for something, but you want the original value of the register back later on, you can use a push instruction to save the content of the register. And then you pop it back later on when you need to retrieve the old value of the register.
Can we have an example on this?
We can have some examples to illustrate the mechanism of push and pop first, and then as we have the necessity, then we'll use push and pop for the applications. Yep.
I'm assuming this is an OS-based thing, correct? The stack?
It is an architecture kind of thing.
Okay.
Because the push and pop instructions are i386 instructions, so it has nothing to do with what operating system you're using. You can be using Windows, you can be using Linux, can be FreeBSD. The push and pop instructions will still do exactly the same thing.
How does that change from, or how is this stack special compared to if we were to make our own stack?
It is not any more special. That's a very good point. Later on in the same chapter, I will talk about what if an architecture, what if a processor does not give you the push and the pop instructions. You can implement your own push and pop instructions. It's really easy to do it. We already have all the instructions necessary to do this. It's just a matter of what is the order of things. That's the most important part. So we'll talk about that. That's a very good question. Yep.
How large is the stack?
How large is the stack? It depends on the operating system. You can change the default size of the stack. I think you can pass a parameter to slash something to the operating system, and you can tell the operating system to change the default size of the stack to a particular size. You can find out pretty easily. You can keep pushing and see when it crashes.
Well, how large is the stack we have in the virtual machines?
It is not the virtual machine that defines the stack size, because when you run an application program, the operating system is responsible to allocate the stack for you. So it has nothing to do with the VM. Obviously everything is in the end limited by the physical memory, but a process doesn't have even close to the physical size of the memory. So the operating system only gives you like a small portion of memory as the stack for a particular process. Do you have a question? Can I answer your question?
Oh, no, I have a question.
Okay, but can you not disturb the rest of the class? Okay.
Yeah.
All right.
Excuse me?
Yep.
So when we copy a file, when we copy and paste a file, it means we're using the top and...
No, that has nothing to do with the instructions. Yep. The instructions, are very specific. So let's go ahead and write a very simple program to illustrate, what push and what pop will do. Okay, so we'll use the debugger to let us, to look into the mechanisms of the push instruction and the pop instruction. Okay. So we'll go ahead and just have one push pop.s here, and this one does not even require a .data section. Eventually, we will write programs that do not require any data data structure, because we want to move away from global variables altogether. Okay, how many people know that the use of global variable is not healthy? 2 hands. Okay. Global variables are evil. I recommend people to add it to their daily prayer. Deliver us,
God,
deliver
please
us
cite
from
all
global
global
variables.
variables.
That's good.
And recursion is your friend.
Sorry?
And recursion is your friend. Amen.
I'm not so sure about that one.
Well,
That's a
Fox.
Mr. Fox thing. Yes. As an embedded system programmer, I try my best to avoid the use of recursion, because in recursion you have no idea how many steps it will take, and when recursion runs out of stack space, the behavior is crash, right? If you write any type of recursive subroutine in an iterative way and maintain your own stack, then you have the ability to check whether it is running out of space or not. And you can control what happens when it does run out of space. You can just say, oh, okay, I'm in a portion of the program that is not important. I'll just return and say, okay, I could not get this computation done, and without crashing the entire program. So that's why in embedded systems where you actually have to predict the size of everything, you don't want to do recursion unless you already know exactly how deep the recursion can go. So I come from a slightly different background from Mr. Fox, and that's why I have a slightly different way of looking at things, which is good. I mean, so now you can see things from both perspectives. All right, so this is a simple, tiny little program to illustrate the use of the push instruction and the pop instruction. So the first one is a push, and I would use an immediate operand, and we'll just push a particular bit pattern here. And I use this one sometimes, feed 0 dad. Okay, because I'm hungry, feed dad. And I'll put it in. Okay, now here's the fun part. Okay, I'll put something else. Push this particular value. Move this particular value into EAX just to make sure that I mess up EAX before the pop instruction. Then I do a pop L into EAX, %EAX, and I call this the end of the program. Then we have the usual exit code, which is not actually needed here because I can always get out of GDB before I get to this part here. But we'll just put it here just for the sake of completeness.
No label?
No label because I'm going to track it down, line by line. So the only one is, I can put a label here so that I don't have to look at the line number. That's the only value of this label.
They have a label 2 lines up. Have a label 2 lines up.
Yeah, but I cannot refer. I cannot say put a breakpoint at 2 lines under that label, or after that label. So there's no way to do that. G-stabs.o, pushpop.o, and pushpop.s. We do the link, and then we run the program. Now this time you guys have to. Yep, go ahead.
What does G-stab stand for? We've been using it all semester, but
I know we're not stabbing something, but
I think the G is GDB, or the GNU toolchain. The S stands for symbol, and then the TAB stands for table. I'm not sure why it is in plural. That's the part that I do not understand. But it has to do with including the debugger's symbol table along inside the object file.
Dash G symbol tables? Dash G symbol tables?
Or GNU symbol table or something like that.
Well, dash G is just what they call all their arguments.
Well, let's see if we can find that out. Generate stabs debugging information. Okay, very good. Okay, that helps a lot. Thank you.
What's stabs plus? Is that better?
Okay, stabs is basically a format for an executable. So so when you generate debug information, it can be stabs, ecof, or dwarf2.
So we can either stab, scoff, or dwarf something.
Or the dwarf2. The dwarf2 is actually a play of the name because in earlier systems they have an elf format. So elf, dwarf, gnome, You can see programmers do believe in those
They've also got
features.
a very weird sense of humor.
is Hobbit next?
Yes.
Yeah.
That's what happens after you write programs for many
We
days
go
without
senile and
sleeping.
write elf
Then you start to
code.
see gnomes walking around on your desk. It's like, okay, I'll call this GUI gnome.
Wait, you mean they're not really there?
I have never been able to verify one way or another. Let's just put it that way. Okay, so we'll put a breakpoint on checkpoint, which is the push instruction. and then we start running the program. This is a push instruction. Now, when you try to understand what a push instruction does, you have to look at the value of the stack pointer, because that's one thing that you want to track. You also want to look at the memory location that is pointed to by the stack pointer. So there are two things for you to track after each and every instruction. One is the stack pointer itself, which is basically a bookmark separating the part of the stack that is in use from the part of the stack that is available. But the second thing you want to do is to see what is the content of the portion that is in use. Okay, so those are the two things that you have to do. So the first thing is easy. If you want to look at the value of the stack pointer, this is the value of the stack pointer before the push instruction. Now, because we don't have any push instruction before this one, I cannot really show you the stack content, because the content before this point is not something that I did. So whatever I display really has no particular meaning. Is that making any sense so far? Yep.
So there may be something on the stack.
Oh yeah. The stack pointer is pointing to some place that actually have some content, and I can show you, how to get to that. You can say x/ if you want to, 20 if you want. It's 20. And most of the time, we push things into the stack in 4-byte chunks, so it makes sense to make it, x, and then in the debugger, I think it's a word. Okay, a word is 32-bit in the debugger, and then you can just specify, $ESP, which is basically a shorthand to get to the value of the register ESP. And this is what is on the stack right now, but none of that is something that I pushed. So it doesn't do me any good, because it doesn't help me illustrate the use of the stack pointer or the push instruction.
Why not pop a few things off and see what happens?
It's not going to be any problem, because we do exit out of the program right away. So none of these will actually matter. Question? Nope. Okay. But for now, this is what we want to know. Okay. We want to take a look at this one here, and then we execute the push instruction. So I single step through this push instruction, and immediately we want to take a look at the stack pointer again. How is it changed from this value to this value? What is the difference? Well, first of all, did I increase the value or did I decrease the value? It's decreased. By how much? What is 0 minus C in hexadecimal? Okay, a 0 is considered like 16, because it is just rounded to 16, and the C is 12, so it's off by 4 bytes. Okay, now it's off by 4 bytes because this is a push L instruction, because the push L instruction is pushing 4 bytes onto the stack, and as a result, the change is 4. But remember what I said, the stack grows down. The stack pointer starts up high. Whenever you push, it becomes lower. This is exactly what I meant by that. Yep.
How low can you go?
How low can you go? I can write a very simple program to find that out. So remind me to do that after this illustration. Okay. So the next thing we want to do is look at the content of the stack. Remember, one way to look at the stack pointer is it points to the very last thing that you push on the stack. So that means if I look at the stack pointer right now and what it points to, I should see feed 0 dead. Okay, that's what I should see. So I would go ahead and do that. Examine, because this is pushing content into memory. Yep.
Is that where you set the checkpoint at? That's why you should see that.
I set the checkpoint, so I can stop the program at the right place. Okay. Well, I just show the memory content that is pointed to by the stack pointer, and we have exactly the value that I pushed onto the stack. Okay. So everything that I talked about earlier, they're all verified here. The stack pointer points to the very last item that you push onto the stack, and 2, the stack pointer moves down. Okay, it starts at a high memory address, and every time you push, it will move down by the number of bytes that you push on the stack. Is that doing okay so far? Yep.
Does the stack pointer ever get updated except when you use a push or a pop command?
You can update it if you want to. You can use a move L instruction and move something into the stack pointer. You can add to the stack pointer. You can subtract from the stack pointer. That's a very good question, because we will use those instructions to implement push and pop so that we don't have to rely on the architecture to support push and pop. Yep.
So what happens if you push the stack pointer up like 50 and then execute the program?
That won't do any harm in this case, because when you request to exit out of a program with corrupted stack content, it's okay, because when you exit, remember, it's a system call to the operating system. The operating system has its own stack, so you can never really corrupt your stack enough to cause the operating system to do something that is haywire. Okay? But if you have your own subroutine, and this is like all the way down to some subroutine call, and you mess up the stack, then really bad things can happen. Remember the first example that I showed you guys, on day one? It's because of a stack corruption. But it was a very surgical mess up, so that it has that particular symptom. But anything that you do wrong on the stack can have very, very bad effect into the program. And I cannot explain that until we have call and return. Okay, are we still doing okay so far, tracking the stack pointer and also what it points to? Okay, so now I single step, which is this instruction here. I initialize EAX to a particular value, and we have EAX being this particular value at this point. The next instruction to execute is the pop L instruction. So we want to find out what exactly is the effect of the pop L instruction. With single step, the first thing we want to do is to take a look at ESP. ESP is now back to what it was, okay? Because if this is the value of ESP before the push instruction, okay? The second thing we want to do is to say, okay, we know we retrieved something from the stack into EAX. What is in EAX? It is whatever I pushed a little bit earlier onto the stack. Okay, are we doing okay so far with the concepts? Yep.
What tells you the location of those numbers? Like, how do you know that one was EAX? Like,
because I wrote a program to pop into EAX.
Oh, so it shows EAX as that inside of your program up there?
Because I wrote the program. This is the instruction. I chose EAX as the register to receive the content from the stack.
Okay,
that's my choosing. That's my choice.
Yeah, that's what I'm saying. Did you already show it, or can I see it again? The program that you wrote that shows pop L as EAX. One more time.
You mean like this?
Yeah. Okay. Sweet. That's okay. There we go.
Yep.
Well, you don't have to pop it into a register, right?
With the 386 architecture, you can pop it into anything other than an immediate operand. But in most RISC architectures, you can only push from a register. You can only pop into a register, because everything else can be done with other instructions. Okay, are we still doing okay so far with this program here? Okay.
Can I see that for like a couple? Can I see that for a couple more seconds to jot it down so I can?
Well, we kind of have to hurry. Sorry, it's all recorded anyway. And I will upload the file too.
Yeah, I just want to be able to follow while you're going right now.
And I made sure that the recording is recording the voice too, so it should be okay. All right, so let's go ahead and write the other program to find out how much we can push before the program bombs out. Okay. In other words, we're trying to find out, what is the amount of space allocated by the operating system so that your application program can play with it. Okay. And that would be a pretty easy one to do. Okay. Stack size. There are easy ways to do it, but this is more fun because we get to crash the program. And this is going to be an infinite loop. So we say push $L $0 JMP start. That's it. That's all we need is an infinite loop that keeps pushing. We can call it pushy. Let's change the name. Now is pushy.
Pushy.o. Sure.
Okay, LD-O, pushy dot O, GDB, pushy. Now this program only makes sense if you run it inside GDB, because if you run it outside of GDB, it will just give you a segmentation fault, but without telling you where the stack pointer is when it gives you the seg fault. When you run it inside GDB, it takes a little bit of time.
A little bit of time.
You've got
Yeah,
a
we can
huge
do something
stack.
else. We can do something else first.
Can you?
Sure, I can.
Wow, that's a
Multitasking. It's a multi-threading, multitasking kernel, man. I mean, this is what we can do.
Got skills, but
I bet you won't break it.
And here's a sample program. And for those of you who have questions and try to write down whatever I wrote earlier, we have the sample program right here. But the point is, you have to trace it. You have to track down this program and take a look at the stack pointer and what it points to in order to understand what it does. This is about the same thing. It's a slight variation of the actual sample program that we went through a little bit earlier. But basically, it's the same thing. Okay. The next one is a more tricky example. We're pushing the flag register, but when we pop it into EAX. So this is a way for me to actually look at the flag register, because normally you cannot access the flag register directly, and this way I can, because I can push it and then pop it into EAX, and I have full access to EAX. Yep.
So is there a way that you can do a compare with the flag register, but redirect it to EAX rather than deflag?
Say that again.
So say you wanted to do a conditional jump.
But
rather than do it based off of EAX, or rather than do it off of the flag register, do it off of EAX?
No, there's no way to do that, because all conditional branches will only look at the C, O, S, and Z flag from the status flag register. So you have to restore something into the flag register before you perform the conditional branch instructions. So let's check back with our program here. It is still pushing. Okay, it has not stopped yet. Now we can always do a Control-C to basically break the execution and just take a look at ESP at this point. Oh, I think we are not even close to being done. And I forgot to take note of the original value of the stack pointer first. So that's not good. We'll just run it again.
Why not take note of where it is now?
Need a breakpoint.
Yeah, we need a breakpoint, but I cannot put a breakpoint on the very first instruction.
So go back and rewrite it.
No. I have 2 instructions. I can still stop it at the jump instruction.
That's going to be slow as hell.
So we'll do a run, yes, IRESP, and then continue execution. Oh, we have to get rid of the breakpoint. Otherwise, I will have to continue every single time it gets to that jump instruction. That will take a while. Okay, so now we can go back. I'm pretty sure by the time we finish in 10 minutes, it would have crashed already.
Get a big stack.
Okay, and here we have a simple sample debug session. So anyone who has read ahead of the class, knowing that we will talk about this topic, can have, this is like blow by blow, okay, description written in text. So there's no need to really go back to the video clip of this class, because this is already describing the whole process. Okay, so let's move on. Okay, so this part is even more fun. The more fun part is to say, okay, let's just say that we don't have a cisp architecture. Okay, we have a RISC architecture instead. A lot of RISC architectures, in order to save the number of instructions, will not give you a push instruction or a pop instruction. So the question now is, without a push instruction and a pop instruction, can we implement the same effect of a push instruction and a pop instruction using instructions that we already know? And the answer is definitely. To implement push ECX, okay, without the instruction push %ECX, this is what we can do. The first thing that we do is we subtract 4 from the stack pointer. The stack pointer was here. We now move it down by 4 bytes. Okay, but those 4 bytes that we just allocated still had the old content. But that's okay, because in the second instruction, we will copy the content of ECX to wherever the stack pointer is pointing to. And therefore, those 4 bytes will now be initialized. It will have the content of ECX. To pop, it is important to know that these 2 instructions are not equivalent to these 2 instructions. They may look the same. Okay, you may look at these 2 and say, but they should accomplish the same thing, because the second implementation will first copy the content of ECX to the 4 bytes below where the stack pointer is pointing to at this point. Then I move the stack pointer down to where it's supposed to go. So when you look at the net effect of these two sequences of instructions, they should accomplish exactly the same thing, with only one exception. The ordering is different. One allocates first, and then it uses the space that it just allocated. The other one uses the space that is not allocated, then it goes back and allocates that space. Okay? So why would this make any difference? What possibly can happen between the instructions?
For some reason, the processor thinks it's being smart in zeroing the memory when you change ESP.
But why would the processor do that?
Because some idiot thought they were being smart and helping us when they did it, when in fact they're making it more difficult.
Okay, I need a more definite answer. It has to do with one of the concepts that we have talked about in the previous class. Yep.
Because if you go to a space of memory you're not supposed to use, then you just wrote into it before you tried to get it.
Do you guys remember interrupts that we talked about on Tuesday? Now, interrupts can happen at any time, including between these two instructions and also between these two instructions. Now, remember when an interrupt happens, it has to do one thing first. It has to save the location to go back to, because it's interrupting a program, and it's using the stack to do that. So that means an interrupt can happen between these two instructions. It can also happen between these two instructions. So how come one is saved from an interrupt and the other one is not saved from interrupts? Yep.
Because if we copy the data onto the stack and then push it down first, when the interrupt occurs, it'll overwrite it.
Exactly. And when the interrupt returns and this program continues execution, it would have no idea that what it put onto the stack is already corrupted. Now, in this case, we allocate it first. Okay. In other words, we say, okay, we moved the stack pointer down already, and these 4 bytes, are not initialized yet. When the interrupt happens, it will just use whatever is below the stack pointer at that point. In other words, it won't mess with these 4 bytes that we are trying to initialize. And then we come back here, after the ISR completes, we'll come back to this point and continue this execution, and nothing bad has happened. Okay, so these two sequences of instructions are definitely different, and one can potentially lead to problems. Yep. It saves a whole bunch of stuff, but the least it has to save is the return address of whatever it is interrupting. Okay, remember what I said, when an interrupt happens, it's kind of like hardware calling a subroutine, and we are kind of out of the scope right now because I haven't talked about the call, but basically a call uses the stack as well. It has its own built-in push inside the call instruction, and that's why we have a problem when we have the second sequence here. Now, what kind of symptom will you experience when we use the second sequence instead of the first sequence?
High fever.
Very sporadic kind of symptom, okay? Because how do you know whether there will be an interrupting this point? You don't know. How do you know which interrupt will be interrupting at this point? Because different interrupts may put different stuff on the stack to change the symptom of this particular bad program. It may not happen for years because nobody clicks on anything, when the program runs. It can happen every minute. It can happen every month. It can happen every minute for an hour, and it never happens for an entire year, and then it happens again. Every time it happens, the symptom can be different. Okay, so this is not the kind of bug that you want to have. Okay, because up to this point, everything that you have done with CISP 360, 400, 430 are deterministic. Okay, we all write programs that have bugs, and we all have to go through the process of debugging. But as long as your bugs are very deterministic, they're easy to debug, because every time you feed the same input to the same program, it breaks exactly the same way. Bugs like this will not give you the same symptom. It's not even reproducible. Okay? Even if you suspect it is something like this, you can try to hit the keyboard as frequently as you want, and you may not be able to reproduce the symptom at all. Okay, so that's why it is a very important topic. And someone in this class is going to try this one out and see whether it will break something that is significant. And the answer is no. Don't even bother to try it because the Linux operating system has a different stack for interrupts. And therefore, this is actually okay to do within an application program in Linux. On the other hand, if you're writing the kernel part of the operating system and you try something like this, then your kernel will be extremely unstable. It will just be crashing left and right and very bad.
How can we fix it?
How can we fix it? We use the first sequence.
No, I mean after you try to do it, and this seems to.
You reboot the system. You fix the program, you reburn the flash image of your operating system, and then you push the power button up again. Yep.
So I just want to get my interpretation of the command, right?
Mm-hmm.
So what it's doing is moving down the address of the stack
Pointer.
pointer,
Right.
and then moving.
And then it copies
What's
whatever is in ECX to where the stack pointer is pointing to.
So would that move down the stack pointer?
No, because this is the first part moves the stack pointer. The second part does not do anything to the stack pointer itself. It will only copy to the memory location pointed to by the stack pointer. Okay. So here we have the full explanation of all that stuff. And let's go back and check the program and see how our rotisserie chicken is doing. All those cook show, they would start, set it and forget it, and then they'll go off and do something else, and then they go back and check on the rotisserie chicken. So our chicken is all done, and so our chicken is all done, and we'll go ahead and try to find out how many bytes are between this number.
Why aren't you just doing IRESP?
Because it has changed. This is the old value of ESP.
Yeah, we want to see the new value so we can see what the difference is.
Yeah, but I want to do the computation all on one single line.
And actually, wouldn't that be already 4 bytes
Yes.
already allocated to?
Yeah, close enough. Argument to parameter operation is not a number or Boolean.
Just put your parentheses in.
Oh, that's right.
It's always the parentheses.
Nope, argument to arithmetic operation, not a number. Okay, well, we'll go ahead and take a look at ISP. To do it the long way. Okay, well, let's see.
Apparently,
at least it's a round number.
80,000 is the
3, 4, 5. And the answer is 8 megabytes or so. So the system pre-allocates about 8 megabytes for the stack. If you run out, it will crash.
That's quite a lot of space, actually.
Not if you do everything recursively. Ask Mr. Fox.
recursion is still your friend.
Recursion is still your friend as long as you have an infinite stack. Yes. Next time you see Mr. Fox, you can tell him that too. Yeah. The stack recursion is your friend as long as you have an infinite stack. Okay, so here, I'm running out of time, but I do want you guys to finish this part pretty much on your own because it's really just the flip side of the other two sequences. This is basically pop. How are we going to retrieve a value from the stack to a register? Okay, so if I want to implement pop ECX but without using the pop instruction, this is how we do it. We just go ahead and copy whatever the stack pointer is pointing to and copy that into ECX. Okay, so we make use of the content, and then we deallocate that space by adding 4 to the stack pointer. Yes?
So we copy whatever the stack pointer is pointing to into ECX. And then
Yes, because this is an indirect operand, this is a register operand.
So we don't put anything into the indirect operand, we just put something into ECX and it'll automatically copy into.
This is an indirect operand. It specifies the content pointed to by the register. In this case, the register is ESP, the stack pointer. And this is a register operand. It means we are just copying into the register ECX. And this is why the operands are so important, the addressing modes, because we are starting to see most of those again. Okay, we are only starting with the indirect, but as we go along, we will start to see some of the other ones, especially the based addressing mode, will basically reappear because it is a handy operand. It's a handy way to perform the operations that we want to specify. So now this time again, it is important that the order is important, because even though these two instructions seem to do exactly the same thing as these two instructions, once again, the problem is, what if we have interrupts happening between the instructions? If interrupt happens between these two instructions, nothing bad is going to happen, because I have already made a copy of that thing here. Besides, at this point between these two instructions, the interrupt will only use the space below the point that I still have the content here. So nothing bad will happen in this case. If I do something like this, I am deallocating the stack content by moving the stack pointer up. When an interrupt happens between these two instructions, then it will use those same 4 bytes and possibly something below that for the interrupt itself. So by the time I get to the second instruction, those 4 bytes would be changed already. So I would have lost the actual content on the stack in the second instruction if an interrupt happens between those two instructions. So that's why the sequence of the instructions is once again important. And once again, we cannot really see the problem. If someone uses this sequence in the program, we won't see the problem, because when an interrupt happens in Linux, it will use the system stack instead of the stack of the application program, and so we won't see the problem. But it doesn't mean that this is the correct order of doing things, because if you use this order to write kernel code where the kernel where the stack is the same with the interrupts, then problems will happen. Okay. Yep.
You signed anyone for today?
Sorry?
Did you sign anyone for today?
Yes, I did. Yep.
So the way to think about this is, don't move the stack pointer until you're done with the data that it's currently pointing.
Exactly. Now, if you guys have just one more minute, I can describe the whole deal pretty easily. What you want to do is to go to the county office to reserve a space before you build a house on that space. Okay, that's the whole idea. You don't want to build a house and then go to the county office, because in the time that you go to the county office, somebody else might have allocated the space that you have built a house already, and go to your space and go, oh, a house is built already, it's mine now. Okay, then you go to the county office and say, I want to reserve that land for my house, and the county office will say, sorry, it's already reserved. You go back and somebody is living in your house, or the house that you built, because it really is not your house anymore. Okay, so remember that example if you want to find out why the sequence of operation makes a difference. So that's the end of today's lecture. Work to start on your homework assignment early if you have problems with the previous one.
It's half done already.
Well, some people might have.